Hello everyone, I am Vamshi from ECD section. My AIT Tech Talk topic is about a converse of Telegan's theorem. Telegan's theorem is one of the most powerful theorem in network theory. Most of the energy distribution theorems and extremum principles in network theory can be derived from it. It was published in 1952 by Bernard Telegan. Fundamentally, Telegan's theorem gives a simple relation between magnitudes that satisfy Kirchhoff's law of electrical circuit theory. The Telegan theorem is applicable to a multitude of network systems. The basic assumptions for the systems are the conservation of flow of extensive quantities, Kirchhoff's current law, and the uniqueness of the potentials at the network nodes, Kirchhoff's voltage law. The Telegan theorem provides a useful tool to analyze complex network systems, including electrical circuits, biological and metabolic networks, pipeline transport networks, and chemical process network. Consider an arbitrary lumped network whose graph has branches and nodes. In an electrical network, the branches are two terminal components and the nodes are point of interconnection. Suppose that to each branch of the graph we assign arbitrarily a branch potential difference and a branch current for, and suppose that they are measured with respect to arbitrarily picked associated reference direction. If the branch potential differences satisfies all the constants imposed by KVL, and if the branch currents satisfy all the constants imposed by KCL, then Telegan's theorem is extremely general. It is valid for any lumped network that contains any elements, linear or non-linear, passive or active, time varying or time invariant. The generality is extended when and or linear operations on the set of potential differences and on the set of branch currents respectively. Since linear operations don't affect KVL and KCL. For instance, the linear operation may be the average or the Laplace transform. More generally, operators that preserve KVL are called Kirchhoff's voltage operators. Operators that preserve KCL are called Kirchhoff's current operators. And operators that preserve both are simply called Kirchhoff operators. These operators need not necessarily be linear for Telegan's theorem to hold. The set of currents can also be sampled at a different time from the set of potential differences, since KVL and KCL are true at all instant of time. Another extension is when the set of potential differences is from one network and the set of currents is from an entirely different network. so long as the two networks have the same topology, same incidence matrix. Telegan's theorem remains true. This extension of Telegan's theorem leads to many theorems relating to two-port networks. Telegan's theorem states that the summation of power delivered is zero for each branch of any electrical network at any instant of time. It is mainly applicable for designing the filters in signal processing. It is also used in complex operating systems for regulating stability. This theorem has been introduced in the year of 1952 by Dutch electrical engineer Bernard D.H. Telegan. This is a very useful theorem in network analysis. Sigma k is equal to 1 and Vk into Ik is equal to 0. If we solve this circuit, I1 is equal to 1.5 amps and I2 is equal to 1 amps. A reference or datum node is introduced to represent the environment and connected to all dynamic nodes and terminals. The matrix where the row that contains element is of the reference node is eliminated is called reduced incidence matrix. The conservation law KCL in vector matrix form. The uniqueness condition for the potentials KVL in vector matrix form. Applications. Network analogs have been constructed for a wide variety of physical systems and have proven extremely useful in analyzing their dynamic behavior. The classical applications area for network theory and Telegan's theorem is electrical circuit. The classical application area for network theory and Telegan's theorem is electrical circuit theory. It is mainly used to design filters in signal processing applications. A more recent applications of Telegan's theorem is the area of chemical and biological process. The assumptions for electrical circuits Kirchhoff's law are generalized for dynamic systems obeying the laws of reversible thermodynamics, topology and structure of reaction networks, reaction mechanism, metabolic networks can be analyzed using the Telegan theorem. Another application of Telegan theorem is to determine stability and optimality of complex process systems such as chemical plants or oil production. The Telegan theorem can be formulated for process system using process nodes, terminals, flow connections and allowing sinks and source for production or destruction of extensive quantities. References. In line references, Telegan's PDH 1952, a general network theorem will the applications, Phillips Research, Penfield P. 1970, a generalized form of Telegan's theorem, PDF, IEEE transactions on circuit theory, CT 17 302 305, retrieved November 8, 2016. Telegan theorem and electrical networks by Paul Penfield Jr., Robert Spence, and Simon Juncker. The the MIT Press, Cambridge MA, 1970. General references: Basic Circuit Theory by C.A. Sir and ESQ, McGraw Hill, New York, 1969. Telegon's theorem and thermodynamic inequalities, G.F. Oster and C.A. Sir, J. Wade, 1971 to 1940. Network methods in models of production, Donald West Watson. Network